Welcome back to my YouTube channel. If this is your first time checking out the video on complex numbers, check link in the description for the first part of complex numbers. So for this class, we'll be looking at trigonometric form of complex numbers. And to look at that, we'll start with the absolute value of a complex number. So the absolute value of a complex value of the complex number represented by z is equal to a plus bi, denoted by the bars, which is absolute value of z, is, so if we have a value of a complex number, the absolute value of it's equal to, we will square the real part and also square the imaginary part, then everything will be under a square root. And this z bar is the distance from the origin to z. Say for instance, if we had an expression of negative 3 plus 4i. So for this one, our absolute value, say this is z. So our z bar for this would be negative 3, we'll square it, plus 4 square, and everything will be under a square root. So this will be 9 plus 16, which is the square root of 25, which is just equal to 5. So sometimes the denotation is that we're given r for the absolute value, so it's the same thing. So this could be represented as r, the distance from the origin. So now let's say we plot this. So for plotting complex numbers, so if we have that and also having that, so this is our imaginary part and this is our real part. So since we have negative 3, and so negative 3 is the real part, so in the real part we'll have a negative 3. Then in the imaginary part we have a positive 4, which is 4i, so we'll have the 4 over there. So let's say our point of interaction where these two are meeting is somewhere here. So that means our z bar or r is this distance here from the origin. So this distance is what we can call our absolute value of z. So that is z is equal to, for all this graph, is negative 3 plus 4i. So this distance that we have can be denoted as r and such. So in any case, if you are told to find the absolute value of a complex number, this is what you just need to apply, this method where you square the real part, you also square the imaginary part, and you're done. If you're told to graph it, just follow the points, the imaginary part and also the real part, and then you get to have a point and you write the absolute value for the same complex. So now looking at the trigonometric form of complex numbers. So if we have this kind of a graph where the representation is coming from a plus bi, let's say z is equal to a plus bi. So that means our a is the real part and our b is the imaginary part. So think of it as us having a b here. So our b is the imaginary part, and the point where they're meeting from the origin is our z bar, which is r, which is the absolute value of z. So if we're to get the sine and cosine for this function, if we start with sine theta will be opposite over hypotenuse, which is r. So that is, we'll have sine theta is equal to, our opposite is b over r, the hypotenuse, like that. And that is, if we were to make b the subject, b will be equal to r sine theta. And then again, if we were to solve for a, cos, which is adjacent over hypotenuse, we'll have cos theta will be equal to, the adjacent is a over hypotenuse, which is r, Making A the subject, we have A is equal to R cos theta. So these are representation. And then our Z, our R or Z bar, we just have, which is R is equal to the modulus of Z, which will just be A squared plus B squared. This will be our modulus of Z, which is R. So now, if we have all these values, if we are to substitute them in the standard form or the rectangular form, so the standard form or the rectangular form of a complex number is this. So now that we have all these variables, if we are to replace them in this expression, we would end up having Z is equal to, so A we replace with the value of A, which is this one. So A is R cos theta plus B, we said B is R sin theta, so that is R sin theta, like that. So if we can factor out R for this case, so that will be R, then we have cos theta plus, sorry, there is I here, plus I sin theta, like that. So this that we've written is the trigonometric form of a complex number. So if we're having Z over there, so this form is what we call the trigonometric form of a complex number. Then it's also called the polar form. In some instances, you find they've abbreviated this form to R, Ci, then S theta. C is for cos, then S is for sine. So this presentation is also just fine. So this is also the polar form or the trigonometric form of a complex number. Then theta is called the argument. So you find some instances I've been taught to find the argument of a complex number. So you use theta to find that value. Then we use tan theta is equal to B over A for us to find the angle. So we'll be using this trigonometric form to be able to find our argument in most cases. So let's look at an example where we have to write this complex number in trigonometric form. So we can identify the modulus. So modulus, we said R is equal to the square of the real plus the square of the imaginary. So in this case, we have -2 square plus the square of -2 again square. That's for the imaginary part. So we'll have 4 plus 4, which is now equal to the square root of 8. We can reduce this. This is 4 times 2, so we'll have 2 square root of 2. So R, the value for R is this. Then we can also look for the angle. So to determine theta, let's use the reference angle. Let's say we'll use alpha. So alpha will be equal to tan inverse of B over A. Remember we said we'll be using tan theta is equal to B over A. In this case, we want to look for the reference angle, so we've used alpha. So alpha is equal to tan inverse B over A, which is our B. Remember our B is the imaginary, our A is the real. So that would be tan inverse of, our B is -2 and our A is -2. So this gives us 1, and the tan inverse of 1 is 45 degrees. So if we're having 45 degrees, so one thing I also need to mention is that if we follow the trig strict methods of finding an angle, we might have two angles, because we might say tan is positive in the first and third quadrant. So we need to sketch it in order to know where our modulus lies. So if we're to sketch the question that we have, this, so we're having that. So this is our imaginary part, and this is our real. So you agree with me that -2 lies here, and also -2, it lies here. So which means our angle, the angle that we have, or modulus first, is formed here. So which means our angle is moving from here all the way to up to there. So our angle is falling in the third quadrant, and tan is positive in the third quadrant. So which means our angle of reference, we're going to add 180 plus 45 to give us the angle that we need, which is 225. So our theta, we'll say theta will be equal to 180 plus 45 degrees, which is the reference angle that we got, which is equal to 225 degrees. So this is our theta. Okay, so now that we have our angle, we also have our modulus r. Our r was 2 square root of 2, and our angle is 225. We can present this as, so our complex number in trigonometric form or polar form will be, so remember the formula the way it was r, then c, is, then theta here. So replacing, we'll have our r is 2 square root of 2, then cis 225, and that's it. So this is fine, or others might present it as 2 square root of 2, then we had, so cos 225 plus I sine 225. So it's one and the same thing, but this is just simplified, so it's better. So then you're done. So that's how you get to write a complex number in trigonometric form. So first you find the r, you find the alpha, then use it for finding your angle, then you're done. Let's look at another example on the same. So if we are given an expression of, let's say z is equal to 4 minus 4i, and we're told to write it in trigonometric form or polar form. So looking at this expression, if we are to, let's say, just identify where it will lie, let's say we graph it. So our 4 is here. So our imaginary part is -4, so we'll have, maybe let's say -4 is somewhere there. So these are meeting in the fourth quadrant. So this is where our r is lying. So let's find the key components. So we need to identify our r, which is this, we square the real plus the square of the imaginary. So that is, we'll have square root of this 16 plus 16, this is 32. Then square root of 32, so which is just 16 by 2, so we'll have 4 square root of 2. So we've broken down 32 into 4 times into 16 by 2, which is 32. So 16, square root of 16 is 4, and then square root of 2 remains. So this is our r, the modulus. Then we can also get our alpha by saying tan inverse of b over a, which is just the tan inverse of our b is -4, and then we have 4 over there. So we have it as tan inverse of -1. So the tan inverse of 1 initially is 45 degrees. So now, since it's negative, in the fourth quadrant, tan is negative. So it's easy for us to get it there, since we are having a -1 here. So that will be 360 minus, so our theta will be equal to 360 minus 45, which is just 315. So now representing everything, so have our trigonometric form will be our r we said it's 4 root 2, then c is, which is cos and sine of 315, and you're done. So that's how you do it. So we have this question, this example, write z, this complex number which is in polar form. We need to write it in standard form or rectangular form. So to solve this, we need to write it in this form first. Okay, so we need to write it in this form. Then after writing it in this form, we can just evaluate the cos and the sine. Then we've taken it to standard form. So initially it's this. So changing it into this format, we'll have 2, which is our r. So we're having cos 120 plus I sine 120, like that. Then we'll have 2. So cos 120 is negative half. Then sine 120 will give us I, then the square root of 3 over 2. Then multiplying 2 throughout, we'll have negative 1 plus I, the square root of 3. And this is in standard form or rectangular form, then you're done. So this is how you change a complex number. If it's in polar form, you take it back to rectangular form. The next part that we need to look at is the product property of complex numbers. So if we have, say, z1 is equal to this and z2 is equal to this. If we were to multiply these two complex numbers in polar form, the product that we get is this. So it's a property that you need to remember. Whenever you multiply two complex numbers of this format, if they're in the polar form, this will be your product always. Then the other part is the quotient property of complex numbers. If you divide two complex numbers in polar form, the result is this. So you need to master this, you need to know it, so for you to be able to solve any questions that will be given, whether to multiply or divide two complex numbers. Let's look at some examples. So we have this example, find the product of z1 and z2 using trigonometric forms of the complex numbers. Then we need to write the final answer in standard form. So that is, we need to convert z1 and z2 into polar form. Then from there we can find the product. So z1 will be equal to, so if we look for our r, so our r1 will be equal to, so the square of the real plus the square of the imaginary. So we have negative 1, we are squaring it, plus the square of the square root of 3. So this is just 1 plus 3, which is 4, which is 2. Then using our reference angle, so tan inverse of, we're looking for the argument, so b over a, our b is square root of 3, our a is negative 1. So this will give us negative square root of 3. The tan inverse of that is 60 degrees as our reference. So the angle is negative, so tan is negative in the second and fourth quadrant. So that will be theta. So in the second quadrant, that is, we are looking at the representation of our complex number. The real the real is negative, the imaginary is positive. So this is falling in the second quadrant. So we have 180 minus 60 giving us 120 degrees. So now that we are having we have the modulus r and we have the angle, the argument is 120, we can write it in this way now. So we said it's r. So now our r is 2. So we have 2. Then CIS of 120. That's for the first part. So Z1 we found it. Now we look for Z2. Z2 we're having negative root 3 over then plus I. So for that one, our R will also be the same. R is 2. Because that is, we'll add the square of negative square root of 3 plus 1 square to just be the same, to be 2. Then our angle will also be, we'll have 1 over the negative of this, and the tan inverse of 1 over negative square root of 3 is 30 degrees as reference, and where tan is negative, it's so our focus again is in the second quadrant, because in this case, if you look at the real part is negative but the imaginary is positive, so we're still in the, this is just the second quadrant, and the second quadrant tan is negative. So again here for our reference angle, theta will just be the same thing, which is 180 minus, so this will be 180 minus 30, which is just 150 degrees. So thus our representation will be 2 CIS of 150 degrees. So now that we have Z1, Z2, we can multiply them since now we have them in polar form. So that will be 2 CIS of 120 multiplying 2 CIS of 150. So from the product of complex trigonometric complex numbers, we're going to use that theorem where we're going to multiply. We'll multiply the two. So from the product property of complex numbers, we're going to multiply the r, which is, we'll have 2 by 2, that is 4. Then we'll have CIS. Then we'll add 120 plus 150. So that is 4 CIS. So 120 plus 150. Okay, we can't even put, so 120 plus 150, that will just be 270 degrees, and we are done. So we'll have 4 CIS 270. So we're told to leave the answer in standard form or rectangular form. So we'll just rewrite it as 4. Then we'll have cos 270 plus I sine 270. Then from here we can find the value of 270. Of course, 270 is 0 minus, and then sine 270 is negative 1. So we just have negative I like that. Then if we multiply 4 throughout, we just have negative 4i, and that's our value. So we have this question. Find the quotient of the two trigonometric values, and then we're told to write the answer in standard form. Okay, so we have this example, which is find the quotient of the two complex numbers. Then we need to use trigonometric forms, and then we write the answer in standard form. So since these are the same values, we just do the same thing. So for Z1, we had found the complex value to be 2 CIS of 120. Then for Z2, it was 2 CIS of 150. So now using the quotient property that I had shown you to find the value here, so write Z1 dividing Z2. So for this one, we'll have 2 dividing 2, which is as 120 minus 150. So that is CIS, 2 divided by 2 is 1. Then we'll have negative 30. So this is the quotient. Then now writing it in standard form, we're going to have will be equal to, so we'll have cos negative 30 plus I sine negative 30. So that is, so we can simplify these two from the odd and even trigonometric fundamental values. So if you can recall, cos of negative x is just equal to cos x, and then the sine of negative x is equal to negative sine x. So going to apply this principle to simplify these two. So that is, so this will just be cos 30 minus I sine 30. And then cos 30 we already know. Cos 30 is 1 over 2. So cos 30 is square root of 3 over 2 minus sine 30 is 1 over 2. So we'll have I 1 over 2. And this is in standard form. We can conclude from here. So thank you very much for viewing this video. See you next time.